Hi, I'm Margie Coleman. Today we're going to work with graphing and finding roots. A root is simply the x value that makes the function equal 0. Therefore, we also call it the 0 of the function. On the graph, it's just the x-intercept. Let's start with an example. F of x equals x squared minus 2x minus 3. Let's graph that on our graphing calculator. So we want to see what this graph looks like, so we're going to enter the function in the y equals screen. So I choose x and then squared minus 2x minus 3. Now I want to get a look at the graph, and it's nice to get a good viewing window to start, and a good place to go is to the zoom button and choose number 6, which is zoom standard. Just press 6. That gives me a nice viewing window from -10 to 10 on the x-axis and from -10 to 10 on the y-axis. Now I want to find the roots for the polynomial, which we said are just the x-intercepts. It looks like there's an x-intercept right here at -1, and there seems to be another x-intercept right here. Looks like 3. So our first guess is that the roots for this polynomial would be -1 and 3. Now we'll just verify to make sure that those are the actual roots. We found -1 and 3 were the roots for this function. So we can verify those by just plugging them back into the function. So first we'll substitute -1 for x. So we have -1 squared minus 2 times -1 minus 3. Remember, when we square a negative number, it always becomes positive, so that's just 1. I have -2 times -1 equals +2, so that's +2, minus 3. 1 plus 2 is 3, minus 3 is 0. So that is a 0 of the function. Now we'll substitute 3 into the function. So I have 3 squared minus 2 times 3 minus 3. 3 squared is 9. Minus 2 times 3 is minus 6 minus 3. So I have 9 minus 6 is 3, minus 3 is 0. So that root also works in the function. Let's try another quadratic example. This function is 2x squared plus x plus 3. Let's see what happens when we put this in the graphing calculator. Again, we'll go to our y equals screen. We'll enter 2x squared plus x plus 3. And let's zoom 6 again. Zoom standard. Look at this function. Notice that the function doesn't cross the x-axis at all. In this case, there are no real roots. In other words, the roots for this polynomial are imaginary numbers, and they can only be found algebraically. So graphically, we can't even find roots to this one. We would have to say no real solutions. Now let's work with a radical function. The square root of x plus 3 minus 2. Let's look at that in the graphing calculator. We'll go to the y equals screen again. The square root is written small above the x squared key, so that means I want to hit second and then x squared to get the square root. It opens a parentheses, so I'm going to take everything that's supposed to be inside the square root and put it inside the parentheses. That would be the x plus 3 part. Now I close that parentheses and put the minus 2 outside the square root, just as my function was written. Let's zoom standard again. This time, it looks like we have a root at 1. So again, we'll take 1 and substitute it into our radical function to see if it equals 0. We found a root at x equals 1. We can verify this the same way. We'll just plug 1 into the function. So we substitute 1 for x. Square root of 1 plus 3 minus 2. That means we have the square root of 4 minus 2. Square root of 4 is 2, So now I have 2 minus 2, which equals 0. So yes, 1 is a 0 for this function. Now let's try a rational example. We have x squared plus 2x minus 3 all over 2x plus 5. Let's put that in the graphing calculator and see what it looks like. We have to be a little more careful when we're entering a rational function. Let's go to the y equals screen. We want x squared plus 2x minus 3 all to be in the numerator of the function, and to do that I have to put it in parentheses. So I open a parentheses and now I put the numerator. So I have x squared plus 2x minus 3 and close parentheses. Now I need my fraction bar, and remember, fraction bar is just division, so I hit divided by. And again, I want the whole 2x plus 5 in that denominator, so I need parentheses again. 2x plus 5. Close that parentheses. Now let's take a look at this function, and I'm going to zoom standard one more time. It does seem to cross twice. One time looks to be right here at -3. The other one seems to be right here at 1. And again, we'll just take these and substitute them in for x in our original function to test to see if these roots work. So we found roots at 1 and -3. Let's substitute 1 in for x in our function. So we get 1 squared plus 2 times 1 minus 3 all over 2 times 1 plus 5. On the top, we square the 1 and get 1. We have 2 times 1 is plus 2 minus 3. So 1 plus 2 is 3, minus 3 is 0. So I know I'm going to have 0 over something, which means that that automatically is going to equal 0. Now let's try -3. -3 squared plus 2 times -3 minus 3. And thinking about what we just said, the bottom doesn't matter on this fraction. The denominator isn't significant. We want the numerator to be 0. So as long as this equals 0, I'll be good. -3 squared, remember that will be positive, so that's 9. 2 times -3 would be minus 6 and minus 3. So 9 minus 6 is 3, minus 3 is 0. So again, I'll have a fraction with a 0 on top, therefore the 3 does work as a root to the function. Let's look at another quadratic example. 14x squared minus 11x minus 15. Let's look at this one in the graphing calculator. So we'll go back to y equals. We'll enter our function, 14x squared minus 11x minus 15. And let's zoom standard one more time. These values aren't as easily identified. This one is someplace between 0 and -1, and this is somewhere between 1 and 2, but it's hard to tell exactly what those values are. Well, your calculator does have a way to give us a pretty good approximation. Above the button that says Trace on your calculator, you'll notice it says Calc, which is short for calculations, and there's a calculation menu we're going to use. So since it's above the button, I have to press second and then press that button to get the Calc menu. And remember we said roots are called zeros? The TI calls it a 0, and I want to find a 0, so I choose number 2. Now when I get back, it's telling me at the top the function that I'm looking at, and that is the function I want. Then it says, give me a left bound. So I need to move so that my cursor will be to the left of the root that I'm looking for, and I'm going to start out looking for this one. So I hit the left arrow button, and the cursor will show up in just a minute. There, you see it coming up, blinking up the screen here. That's to the left. So now once I'm to the left of it, I hit enter to say, yes, I found you a left bound. Now it says, okay, I want a right bound. So now I have to move the right arrow to get to the right of that point. And that is to the right of the point. I like to go at least twice past. Hit enter. And then it says to guess. Some functions cross more than once, and so it always gives you the opportunity to get closest to the one you want. And that's about as close as we can get the way it's jumping. So we'll hit enter again for our guess. Notice it jumped right to the root, and it gives me a decimal equivalent for the 0. It's negative 0.7142857, and it probably continues from there. But that's a decimal approximation of that root. Let's go ahead and find the other root that's over here somewhere between 1 and 2. So I'll say second, and press that trace button again. Choose number 2 for 0. Now I'm already to the left, but I don't like to be that far to the left, so I'm going to go over to the right a little bit closer to it. As soon as it comes on the screen, as soon as I can see the cursor, I'm going to stop. There it is. So that's to the left. So I say enter. Yes, that's a left bound. Now I have to move to the right, so I'll hit a couple times to the right and say, yes, this is a right bound. Enter. Now I want to move back toward the root, so I hit the left arrow to get back toward it a little bit. For my guess, yes, that's my guess. Enter. And it gives me a pretty good guess of 1.5. So it very likely is 1.5, but of course, we're going to want to go back and double check just to be sure. Since we're working with polynomials, if the roots are rational, there is a way to find exact values, and we don't have to be stuck with the decimal approximations from the calculator. We're going to use the rational root theorem. The rational root theorem is a way to create fractions of the form p over q. The values for p and q come from factors of different terms in the function. P values are all the factors of the constant term, which in this case is 15. It's the term with no variable, and we can ignore the negative. So the factors are 1 and 15, 3, and 5. The values for q are the factors of the leading coefficient. The leading coefficient is the number in front of the term with the largest exponent. Since our largest exponent is 2, the leading coefficient is 14. So its factors are 1 and 14 and 2 and 7. Now we're going to build our fractions of the form p over q. Every possible value of p over every possible value of q. And we want to consider positive and negative values. So we'll just write plus or minus, and then 1 over 1, which is just 1. So we'll write it in the simple form. Then plus or minus 1 over 2, and plus or minus 1 over 7, and plus or minus 1 over 14. Now we'll do the same thing with our 3. We'll have plus or minus 3 over 1 is just 3, then plus or minus 3 over 2, then plus or minus 3 over 7, and plus or minus 3 over 14. Doing the same thing with 5, plus or minus 5 over 1, which is 5, plus or minus 5 over 2, plus or minus 5 over 7, and plus or minus 5 over 14, and finally the same thing with 15. Plus or minus 15 over 1, plus or minus 15 over 2, plus or minus 15 over 7, and plus or minus 15 over 14. Now we have a very long list of fractions, and we certainly don't want to check every single one in our function, but this is where we use the graph. We'll zero in on which ones seem feasible. And the first thing to remember is when we looked at the graph, we noticed a root between 1 and 2. So let's just look through our list of fractions and find values between 1 and 2, such as 3/2. and we would focus on the positive one because this was on the positive side of the y-axis. And the other one is 15 over 14. That's just slightly bigger than 1 as well. So one of those two fractions very well may be that root that we noticed between 1 and 2. So now we just want to check to see which one it is. We could plug them in for x or substitute for x like we have been doing, but there is another method that we can use with polynomials called synthetic division. And here's how it works. Whenever I have a value that I think may be a root, I write it down and put it in a little half box. Then I list just the coefficients of the function. So I have 14, negative 11, and negative 15. Now, leave some space and draw a line across. Here's the process. I just bring this 14 down and write it at the bottom. Now I take 14 times 3/2, which gives me 21, and I put that in the next column. Now I add the column, which gives me 10. I multiply 10 times 3/2 and put that in the next column, and I add the column, which gives me 0. This 0 is the remainder of my division. Essentially, I just divided my original function by a factor x minus 3/2. If my remainder is 0, then that really is a factor of the function. Therefore, 3/2 really is a root. So I know this is one of the roots for my polynomial. I know 15 over 14 must not be because there was only one root between 1 and 2 when I looked at the graph. Now I could go back to the long list of fractions and start searching for more that lie in the correct place and do all this synthetic division again, but I do have a shorter way. Now that I started with quadratic, when I divide out one binomial, that leaves me with linear. So now I have 14x plus 10. And all I have to do to find the other root is set this equal to 0 and solve. So I subtract 10 from both sides, and I get 14x equals negative 10. And I divide both sides by 14. So I get x equals negative 10 over 14. And I can just simplify that fraction, dividing top and bottom by 2. And I get negative 5 over 7. And this is the other root for the polynomial. So now I have exact values. Finally, let's work with a cubic polynomial. X cubed minus x squared minus 9x plus 9. Let's put this one in the graphing calculator and see what we find. Now let's take a look at this cubic. So I go to y equals, and I enter my polynomial. Now, I don't have a nice little x to the third button, do I? But it's very easy. We can use this caret button to say, here comes an exponent. So I'm going to put my x, and then say, okay, here comes an exponent, and then my exponent is 3. Minus x squared minus 9x plus 9. And again, I'm going to start out with my standard viewing window. This time, looks like I have a root right here at negative 3. There seems to be one here at 1, and another one here at 3. So now I have to verify all 3 of those roots. Again, we can test these 3 roots by substituting them into the original polynomial, or we could use the synthetic division that we just talked about. I'm going to try that one. So I want to test if 1 is a root for this polynomial. So I put 1 in the box. Now I list the coefficients. My x cubed term has a coefficient 1. My x squared term has a coefficient negative 1. Then I have negative 9 and 9. Draw my bar. I bring down the 1. 1 times 1 is 1, and I add, which is 0. 0 times 1 is 0, and I add, which is negative 9. Negative 9 times 1 is negative 9, and I add, which is 0. So yes, x equals 1 is a root. Now I can start again, or I can just use this row and try negative 3. but I only have to go to here. Bring down the 1. 1 times negative 3 is negative 3, and I add. Negative 3 times negative 3 is 9, and I add, and I do get a 0, so that one works. The last one I have to check is 3, and you can either just write x minus 3 equals 0 and solve, or you could do another level of synthetic division. At this point, it's probably just easier to add 3 to each side and see that, yes, 3 is the other root for this polynomial. In summary, today we talked about finding roots for polynomial functions. In general, we were finding them from the graph. Usually you can just look at the graph, see where it crosses the x-axis, and that would be your roots of the polynomial. We can also verify those by substituting those values in for x in the function, or by using synthetic division if it happens to be a polynomial function.